Hello. Good morning, everyone.
Yes,
Hello,
sir.
can you hear me, please?
Yes, we can hear you.
Just wait. That I have to share my screen. Just wait for a few minutes. From my laptop, I will share. Just wait.
1 minute, sir.
Just a minute. Sir. Hello.
Yes, sir.
You just send me the link on my mail so
Which
that
link,
I can
sir?
open it on the laptop also.
Yeah, I already mailed, sir. I already mailed you.
Not able to find it.
Okay. Wait, just I will send you once again.
So that I can share my presentation.
Zoom link, no?
Zoom link.
Yeah.
On email, you send me on my email.
Yeah. Yes, I have sent you, sir.
Just a minute.
Good morning, sir. Sir, your name is here F1DDBDAE.
Yeah, that is a mobile number.
Okay.
So I need both mobile as well as
Okay.
other one that I will now join.
Sir, I'll start the session till you get that mail and you share.
No problem, you can start.
Okay.
But when I join from my laptop, you just allow me.
Yes. Yes. Again, I will make that co-host and again. Okay, sir.
Yeah. Chaudhari, sir, you got the mail, sir?
Yeah, yes, I got the mail.
Yeah, okay.
I'm trying to connect it from laptop so that I can share my presentation.
Yes.
Are you able to see my screen?
Yes, sir.
Yes, we can see, sir.
Yes, sir. We can see the screen. Shall I start, sir?
Yes, no problem.
Okay. Good morning, everyone, and a warm welcome to the last session of this workshop. It's a great honor to introduce our guest speaker of this session, Professor Shrikant Chaudhari. Professor Chaudhari has done his graduation in 1981 from University of Pune and post-graduation in 1994 from North Maharashtra University, Jalgaon. He did his MPhil in 1996 and PhD in 2003 from Shivaji University, Kolhapur, under the guidance of renowned Indian mathematician Dr. H.V. Kumbhojkar. He started his career as a faculty from Elphinstone College, Mumbai. He joined Shivaji University, Kolhapur in 2006 and remained there till 2014. Later on, Sir joined North Maharashtra University, Jalgaon as the head of the Department of Mathematics in 2014 up till now. Professor Chaudhary has 24 years of teaching experience. Sir has guided 1 MPhil and 7 PhD students. His area of research is algebra and fuzzy mathematics. He has around 40 research publications to his credit in various national and international journals. He has successfully completed 2 major research projects funded by UGC. He is a life member of various mathematical societies such as Indian Mathematical Society, International Society for Rough Sets, Bharat Ganit Parishad. Sir has co-authored 3 books at PG level. He has worked as a referee for various international journals, also as a subject expert for evaluation of MPhil and PhD thesis of many Indian and foreign universities. He has delivered more than 100 talks in various national and international seminars, conferences, and workshops. He is a member of Board of Studies in Mathematics of many institutes, including our RJ College. In 2015, he received Mahatma Jyotirao Phule Adarsh Rashtriya Shikshak Purashkar from the government of Maharashtra. These achievements are just tip of the iceberg. His accomplishments are enormous and overwhelming. With this, on behalf of our Department of Mathematics and participants, I welcome you, sir, and request you to begin your session on historical development of number theory. Over to you, sir.
For your nice words. I don't think that I'm much capable of what you read out, right? It's just academic. And in the beginning, I'm very much thankful to RG College and principal and head of the department for giving me an opportunity to share my views in front of you on number theory and historical review. Very important thing is I'm not a man who has studied history of mathematics, or neither I have taught the course to any of the students. As Professor Tikare called me 8 days or 10 days before and asked me to give some lecture either on algebra or number theory. Algebra was my first preference, but I thought that I should talk to you on number theory. Number theory as such is not there in the beginning when the mathematical thinking was started. So you cannot differentiate number, history of number and history of mathematics from each other, right? And one more thing is whatever content I have taken it from a book, right? From a one book which is published by Mr. Bell, right? So whatever content is there, I myself is not claiming that I have done something or that, or whether it is exactly correct or not. Whatever periods and dates are given, those are approximate, I suppose, and whichever are given in that book that I am giving to you, right? So this. So let me start with this one. Just see this one. Nothing I want to say.
Sir, sorry to interrupt you. Just can you make your that PDF full screen?
Your screen.
Means in that view.
Yes.
File edit view option. There is option for full screen.
Okay. You cannot see it in the full screen, but
actually means this it is blurred.
It is there full screen on my mobile. So
sir, in this view option.
Yes.
In the PDF, there is a view option, view edit file. Okay, in that view option, there is option for full screen. Yes, sir.
Okay, okay, understood. Full screen.
Full screen, full screen.
Okay.
Yes, sir. Thank you, sir.
Okay. The positive integers are undoubtedly man's first mathematical creation. You can think about like this. So that was the first numbers are the integers, positive integers are the first that came when mathematical thinking was started. It's hardly possible to imagine human being without the ability to count at least within a limited range at the beginning. Historical record shows that as early as 5700 BC, the ancient Sumerian kept a calendar, so they must have adopted some form of arithmetic. So you can see that 5000 BC. So now it is 2021. So this is AD, right? And now I'm talking about BC. So before first we go back to 5700 years before one. So that time Sumerian calendar was there, and so it is believed that some arithmetic they have done at that time. So it was 5700 plus 2020 we can add. So that much years in the history mathematics was the arithmetics was there. It was just roughly calculated, or it was mentioned in the book. By 2500 BC, the Sumerian had developed a number system using 60 as a base. Now, whatever mathematics we are doing, that 10 is a base. That time it is 60 as a base. And there are so many cultures where this base was different, right? Sometimes it is 20, sometimes it is 10. So, in different cultures or different civilizations, the base was different. So, this is about 2500 BC. Sumerians were using 60 as a base for their arithmetic, right? This was passed on to Babylon. So after Sumerian, whatever arithmetic was there, it was passed on to Babylonians, who became highly skilled calculators. Babylonian clay tablets containing elaborate mathematical tablets have been found during dating back to 2000 BC. So you can find out, people have found out those tablets, clay tablets, on which some mathematical thinking was written in their language, you can say. So that was found 2000 years in BC, right? Numbers were used for keeping records and commercial transactions for over 5000 years before anyone thought of studying numbers themselves in in systematic way. So anybody can think that numbers were started studying systematically. Before that, 5000 years before that, you can thought that numbers were there and they were used for commercial transactions. The first scientific approach to the study of integers is that the true origin of the theory of number is generally attributed to Greeks. So, if you thought about integers, then probably it was started during this Greek period around 600 BC. See, around 600 BC, Pythagoras and his disciples, that means his students, or we can say members who were studying with him, or he was the followers, we can say, of Pythagoras. Those were there, right? So this is regarding the somewhat history which is there. Pythagoras itself was studying these numbers, integers in this way. Even numbers, odd numbers, prime numbers, composite numbers. Whatever numbers are written, 2, 4, 6, at that time these symbols were not there. So they were studying integers and all the sort primes and primes in the form of some symbols which were there at that time, right? Now it is interpreted as 2, 4, 6, and so on, the symbols, right? That now we are using. But this Pythagoras and his followers also using this numbers, which are odd, even, primes, and all those things, right? This is a period of, this was in Greek period. Now we'll talk about something in Greek period, which mathematicians were there or which astronomers were there, was studying integers or numbers, right? So we talk about them first. We see that what they have done and what was their topic at that time. Right, in Greek period, you can see Thale was a man. Thale was a person who born in millets, and he was his period life period was 640 BC to 550 BC. This is approximate period, right? Exact numbers nobody knows, right? And this Thale was known as one of the sagas of seven sagas of Greece. The sagas means well-known persons in the history of Greek, and they think that seven people have contributed in their history, right, in their civilizations. So Thale was one of them, right? So you can see there are two columns in my presentation here. In the first column, you can see that I'm talking about the uh, uh, mathematician or astronomer Thale, and in second column, something regarding to his mathematics, right? So in the right column, we can have mathematical studies done by this mathematician or astronomer, and left hand side column will contains his life history. That is related to number only I have taken. Related to geometry also, some figures were there that I have not taken. This Thale is known as a founder of the earliest Greek school. That school was known as Ionian school, right? That time they are talking about like this. Actually, the school which were existed now, such schools were not there. They may be of the form of some ashrams and all those kind of things.
ఏ వద్దు వద్దు ముట్టుకోకు క్లాస్ నడుస్తుంది
So,
ఆఫ్ చేసావా
somebody, hello, can you please mute your speakers? Participant, please. Okay. He engaged partly in commerce and partly in public affairs. Thale was partly in commerce and affairs, public affairs. Thale first went to Egypt as a merchant because he was a merchant, so he went to Egypt. During his free time, he studied astronomy and geometry. At time these were there. So he abandoned his business and public life and devoted himself to the study of philosophy and science. Actually, philosophy was there before this astronomy and geometry and all this, right? So whatever is there in the form of philosophy was there at that time. So he has left his business and he started taking interest in mathematics and philosophy and science, right? Thale wrote on astronomy, and among his contemporaries, he was more famous as astronomer than geometrician. He used to thought that a year contains about 365 days. So he was man who is thinking about the year contains 365 days and not 12 months of 30 days each. That time people were thinking like this. So year is of 12 months and 30 days. So if you take it like this, then it will be 360 days only. But Thale was thinking that it is about 365 days. To his observations and all this. He believed that the earth to be a disk-like body floating on a water. Right? That is what he believed, right? It's not believing that it is a circular shape, but he thought that it is a disk-like and floating on water. So, based on this observation, he has made some calculations or some mathematical thinking or philosophical thinking. Now you see on the right hand side column, the angles at the base of an isosceles triangle are equal. Angles at the base of the isosceles triangles are equal. So if you take an isosceles triangle, then the base angles will be equal. That is what is his observation. If two straight lines cut one another, the vertically opposite angles are equal. So that is what he has obtained, and that is what he has teaching. So right now also you can see that if two lines are to cut each other, opposite angles are equal, right? A triangle is determined if its base and base angles are given, right? So angle can be determined based on the base and base angles are given. And this is used by himself. You can see in this bracket, this was applied to find distance of a ship at a seat, right? The base being a tower and base angle being obtained by the observation. So tower can be treated as a base, right? And angle observation angle can be treated as the angle of the. So the distance of a seat can be calculated using this mathematical technique. The side of equiangular triangles are proportionals. So we find out and prove that the angles are proportional. These have been used by Thales in Egypt to find the height of a pyramid. When he was in Egypt, so he has used this to find the height of pyramid. Right? So this the sides of equilateral triangles are proportional. So we thought that they are in proportional, so height can be calculated. After that, so you can see the period of this Thales, 640 BC to 550 BC. There are other geometrical and astronomical uh, observations and calculations were there that I have not taken. I have taken only those are related to numbers because I want to talk about numbers only. Pythagoras born in Samos in 569 BC to 500 BC, right? So if you go back from 0 to other side, so the years will be 569 to 500. So it will be decreasing. Generally, we say that 1900 to 1921. So next number is increasing. No? So in BC, the numbers are like this, increasing first and decreasing later on. So you go from 0 to onward, right? So the reverse side you can, so that period you can calculate, right? So he was also a merchant, and he has some interest in mathematics. To get knowledge of mathematics, he has traveled so much. You can see here, Samos. He was in Samos, and then he went to Thebes. Then he went to Memphis in Egypt. Then Asia Mentor. Then he came back to Samos, and then he went to Sicily. Then Tarentum, and then Creton in Italy. Right? Tarentum was a big place where mathematics was developed so much at that time. After coming to Creta, he opened a school known as a Pythagorean school, right? His wife, Theano, daughter of his host below, wrote a big biography of her husband. That means Pythagoras, but unfortunately it is lost. So the biography was not there. He divided his attendee into two classes, right? His followers, he divided into two classes. Uh, some of them are called professionals and others are called Pythagoreans. Only to the Pythagoreans that his chief discoveries were discussed. So whatever his discoveries are there, those will be circulated or those will be discussed with Pythagoreans, right? Not to the professionals, right? So that is what was there. Pythagoreans forms a brotherhood, right? So they form a group, you can say, with all things in common. So everything is common for them, holding the same philosophical and political belief, engaged in some same pursuit, and bound by oath. So they have taken an oath not to reveal the teaching or secrets of the school. So whatever secret is there, whatever teaching are there, that means whatever discoveries are there, that should not be discussed with the other people, right? Should not be discussed with the other. Only among the Pythagoreans they have discussed. So that makes something like this. They thought that they are the only thinkers, they are the only wiser people. And due to this strict discipline and secret organization gave the society a temporary supremacy. So they thought that they are supremized now, right? And as instigated by his political opponents. So now that divide the society into two groups, supremum people and non-supremum people. And you know the tendency of non-supremum peoples, right? Because there is a discrimination. So they thought that these people are not good, suppose something like this. So as instigated by the political opponents, the mob murdered Pythagoras and many of his followers, right? So might be there is something, some kind of utha or something like this, and they have murdered Pythagoras and his followers, right? So this was there. I will go back to the next slide. I will go to the next slide so that I can read out the lifespan, and then we'll come back to mathematical thinking. They re-established themselves at once as a philosophical and mathematical society, and continued to flourish for more than 100 years. After this also, they have re-established themselves for hundreds of years. Right? Pythagoras himself did not publish any book, so he has not written any book. The assumption of this school was that all their knowledge was held in common and held from the outside. So they are not uh, giving it to the others, and that is a common knowledge. He has not written any book as such that this is my work, something like this, right? Hippasus, we can say, 470 BC, is said to have been drawn or violating his oath. So he was his follower, right? After Pythagoras, he was the boss of that school, right? So he was drawn for violating his oath by publicly broadcasting that he had added dodecahedron to number of regular solids enumerated by Pythagoras. Whatever Pythagoras has found out solids, regular solid. Apart from that, Hipparchus has added dodecahedron. That dodecahedron we know is a 12 face equal side 12 face body, right? So which he has added, right, to the discoveries of Pythagoras. He publicly said so. That's why other people has known him, right? Thing like this. By the end of 5th century BC, their more prominent discoveries and doctrine had become known to the outside world, and the center of intellectual activity was transferred to Athens, right? So that is after the date of Hipparchus and Pythagoras, the knowledge becomes public, and the discoveries were discussed with the people also, right? And after that, the intellectual activity go to Athens, right? Let us see what are his things about mathematics. After scattered them, the first book was composed in 300 BC. Because after death of Pythagoras and Hipparchus, all these people were scattered, right? Pythagoreans are scattered. And the first book was composed in 370 BC by Philaus. And it is believed that the copy of it is with the Plato also, right? Plato secured a copy of it. Whatever book was written, the copy was there with Plato. Plato came later, right? The glory of Pythagorean school that is that they believe that they raise arithmetic above the needs of merchants. So not only for calculating the things which are there in, regarding merchant, but they applied it to calculating the other things also. Similar, that means calculating the distance of a ship in the sea, or you can say distance of a pyramid, or maybe a distance of a moon from the earth, and so on, right? So they have, they have more elaborated thing of arithmetic they have done. It was their boost that they sought knowledge and not wealth. So Pythagoreans sought knowledge, not the wealth, right? So that is what the belief is there. The Pythagoreans divide mathematical subjects into 4 divisions. So they divide numbers into 4 categories. Numbers absolute or arithmetic. So that is the first class of numbers, you can say. Arithmetic, you can say. Number applied or applied numbers, or you can say music. So they have divided subjects into different categories: arithmetic, then music, then magnitudes at rest or geometry, you can say, and magnitudes of motion or astronomy, you can say. So they categorize in the 4 ways. That means arithmetic, music, geometry, and astronomy. So they divide into 4 classes. In geometry area, Pythagoras taught contents of the first 2 books of Euclid about parallels, then triangles and parallelograms, right? So Euclid came late, so much later, right, in the history. But he wrote a book, right? Actually, a series of books which contain 13 books, right? So whatever was compiled by Euclid, that was Pythagoras was teaching at that time. He was existed, right? So in geometry area, he taught about parallel lines and triangles or parallelograms and so on, right? Precisely the following for regarding numbers. A number of definitions connecting mathematical ideas with philosophy. So he has given definitions which connects mathematics and philosophy, right? The sum of the angles of a triangle was shown to be equal to the right angles. You can see that addition of all the angles of a triangle is equal to 180. So right angles, 2 right angles I mean. So 90 plus 90 is 180. So sum of the angles of a triangle is 180. That is what it was there in geometry. He used to taught it to his students, or you can say followers. He proved the properties of right angle triangles at that time only. The plane about a point would be completely filled by equilateral triangles. That is what he said. Plane can be filled out with triangles, or say squares, or say regular hexagons, and so on. In number theory, Pythagoras studied the following: polygonal numbers. Right? Polygonal numbers, we know that numbers represent in geometry with the form of a endpoints of a lines. Right? So polygonal numbers. Ratio and proportion was also studied that time. The factors of numbers, that is also there, and numbers in series. So series form is also there. Polygonal numbers and proportions were treated by geometrical methods. So numbers were treated in the form of geometry, right? Geometrical objects they are treated. Pythagoras commenced his theory of arithmetic by dividing all numbers into evens and odds. So he used to divide the numbers into even and odd. See one of his discovery in numbers, the odd numbers being termed gnomons, right? G is silent, I suppose. The odd numbers being termed gnomons, not nomens. Gnomons. These are odd numbers, I mean. Gnomons, whenever come, you say odd numbers. An odd number, such as twice n plus 1, was regarded as the difference of two squares numbers, right? Difference of this one. So if you take the n plus 1 square and if you simplify it, you can see now it is n square plus twice n plus 1. And now subtract n square. So it will be twice n plus 1, right? So that time he was regarding this odd numbers as like this. Because if you put n is equal to 1 or n is equal to 0, then it will be 1. So that is the first odd number. When you put n is equal to 1, it will be 2 into 1 plus 1. That is 3. And if you put 2, then 2 into 2 plus 1, 5, and so on. So these numbers are treated as twice n plus 1, and which is the difference of these two square numbers, n plus 1 square minus n square, right? Like this. The sum of the nomens from 1 to twice n plus 1 was stated as a square number. So he defined the square number like this: sum of the odd numbers, right, from 1 to twice n plus 1. And n plus 1 square, its square means like this, n plus 1 square. Its square root was termed as a side, and the roots are termed as the sides of the geometrical object. Now see, 1 to twice n plus 1. So if you put n is equal to 0, this is 1 to 1 it is, right? Twice 2 into 0 means 0. So 1 to 1. So if you put n is equal to 0, this sum will be from 1 to 1 itself. Only odd numbers you have to take. So 1 is odd. So 1 is the sum. And you can say this is 1 square, right? So this is first square, you can say. When n is equal to 1, you can see 1 to 2 into 1 plus 1. So 2 into 1 plus 1 is 3. So 1 to 3. But odd numbers only you take. 1 and 3. So 1 plus 3 is 4. That is square of 2. This is when you put n is equal to 1, it is 1 n plus 1 square. So 1 plus 1 square. 2 square. Similarly, if you put n is equal to 3, it is 6 plus 1, 7. So 1 to 7, you take only odd. 1, 3, 5, 7. You add 1 plus 3, that is 4. 4 plus 5, 9. 9 plus 7. Right? 9 plus 7. 16, it is 4 square, right? Something like this. So this sum of the nomens from 1 to 9, this was studied, right? And it is nothing but square. Product of two numbers were called plane. So in geometry, they represent it like this. So product of plane, and if the product had no exact square root, it was termed as a oblong, right? A product of three numbers was called a solid number, and if the three numbers were equal, it is called a cube, right? And when we put them in geometrical form, whatever that way they represent it, so actually this look like say triangle and squares and like this. So that's why they term the definition like this, right? A product of three numbers was called a solid number. If three numbers were equal, it is called a cube. All his obvious references to the geometry, right? And opinion is confirmed by Aristotle later on, and he remarked that when a genome is put around a square, the figure remains a square, right? Though it increases dimension. So geometrically, you can see if it is given in the book in a more elaborative way, If somebody want, he can go to that book. I will give you in the reference which book it is. So you can see the diagrammatical form also there in the book, and you can understood what it is. The numbers 2n square, it is actually 2n square, not 2n2. 2n square it is. 2n square plus twice n plus 1. 2n square plus twice n and 2n plus 1 possesses special importance as representing the hypotenuse and two sides of a right angle triangle. Right? So these three numbers, 2n square plus 2n plus 1, this is the first number. The second is 2n square plus twice n, and the third one is twice n plus 1. So one of them is hypotenuse and the other two are sides of a right angle triangle. So if you put n is equal to 0, you see what are those numbers. When n is equal to 0, it will be the value, the first value will be 1, second value will be 0. So I think you don't put 0, you put 1 or something. 1 after 1 you start. So when n is equal to 1, this will be 2 plus 2 plus 1, that is 5. And then this number is 2 plus 2, that is 4, 5, 4, and then this is 2 plus 1, 3. So 3, 4, 5, you can see. And 3, 4, 5, you can see that 3 square plus 4 square is equal to 5 square. So these are the numbers. So they are the number obtained as a Pythagorean triplets. So you can obtain Pythagorean triplets from this, right? 2n square plus twice n plus 1. This is the first number. Second one is 2n square plus twice n, and then 2n plus 1, right? So they were studying these numbers in this form. A more general expression for such numbers is m square plus n square twice mn and m square minus n square. But these are not exactly what it was given when I calculated it. If you put m is equal to n plus 1 here in these three numbers, m square plus n square twice mn and m square minus n square, if you put m is equal to n plus 1, you will exactly get the numbers which Pythagorean is giving, right? To be n square plus twice n plus 1 and all those, which are there in the above bulleted point, right? So these numbers are Pythagorean triplets. After we can obtain all Pythagorean triplets from this. Pythagoras himself acquainted with triangular numbers. We know what are triangular numbers. When we put dots with a decreasing order, increasing order, one you place on the beginning, and then two on the next row, three on the next row, fourth on the next row, and so on. You get a triangular diagram. Such numbers are the triangular numbers, right? So dots you can calculate. Number of dots, total number of dots is called that number is called a triangular, right? So a triangular number represents the sum of the numbers counters laid in a row on a plane. The bottom row contains n. That is what I'm saying. You start with 1 in the first row, 2 in the second row, 3 in the third row, 4 in the fourth row, and so on. So that way it is. So you take n is equal to any number from 1 to onward. When you put n is equal to 1, so there will be only one row which contains one element. So 1 is a triangular number. And when you take two rows, so on first row, in the first row there is one dot, and in second row there are two dots. So if you take two rows, then 1 and 2, 3. So 3 is a triangular number because it is triangular. If you take four numbers, number 4, then on the first row it will be first dot, on the second row there will be two dots, and one more dot will remain that you have to put in the third row, and that row is incomplete, right? It is not containing 3 dots because you have to increase one element in the next row, no? Something like this. So that 4 is not a triangular number. 6 will be the next triangular number, and right. You can see that it is therefore equal to the sum of the series. So sum of this n in n plus n minus 1 plus n minus 2 plus 2 plus 1, something like this, and that is equal to 1 by 2 into n plus 1. So in this formula, if you put n is equal to 1 and so on, you will get all triangular numbers. So n is equal to 1. This is 1 into 1 plus 1, right? 1 into 2, I mean 1 into 2 is 2 into multiplied by 1 by 2. So 2 get cancelled, it is 1. So when you put n is equal to 1, you get 1. That number is a T1, you can say. That is the first triangular number. T2 you can obtain while putting n is equal to 2 in this formula. So 2 into 3, 6. 6 divided by 2 is 3. So 3 is that number. Next you can put 3. 3 into 4, 12 divided by 2, 6. 6 will be the next triangular number. When you put n is equal to 4, 4 into 5, 20 by 2, that is 10 is the next triangular. So you can this way you can calculate all triangular number. So triangular number regarding 4 is 10, something like this, right? So they are treating those triangular numbers that time. The Pythagoreans are said to have classified numbers by comparing them with their sum of their integral divisors, or subdivisors, or factors, we can say. Pythagoreans, I mean, those are the followers of Pythagoras, right? Pythagoras and the followers, right? All, I mean. So subdivisors are factors they are calculating, calling a number excessive, perfect, and defective. According to the sum of these divisors or factors was greater than, equal or less than the number, right? So you have to see the example. 8 is a defective and 12 is a excessive number. If you take the divisors of 8, don't take 8, right? Less than that. So what are the divisors of 8? 1 is the first divisor, 2 is there, 1, 2, then 4, right? 1, 2, and 4. You don't take 8. So add 1, 2, and 4. 1, 2, and 4. 4 plus 2 and plus 1. 7. That is less than 8. So this is less than 8, so less than the number, and therefore it is defective. But you take 12 and add the divisors. It is bigger than 12. And therefore it is excessive number. And when it is equal, you say it is, the number will be perfect number, right? Numbers are something like this. So they treat numbers like this. Pythagorean deals with numbers which form, just a minute. Yes, Pythagorean dealt with numbers which form a proportion. Presumably, these were discussed with the aid of geometry, as done in the fifth book of Euclid, right? In fifth book of Euclid, it is given in more elaborative way, and those numbers they were treating. The Pythagoreans were concerned with series of numbers in arithmetical, geometrical, harmonical, and musical progression. So they were discussed series, but in the form of arithmetical progression, geometrical progression, harmonical, and musical progression. Right? You might have already studied, or you might be teaching arithmetical, geometrical, and harmonical progression. But there is one more progression, is that musical progression. So at that time they were discussing about those series of numbers. Integers are said to be in musical progression when they are in the ratio a as to twice ab. That equal is not there, divided by twice ad divided by a plus b. So a as to twice ab divided by a plus b, as to 1 by 2 a plus b, and as to b. So a and b at the extreme ends, a at the beginning and b is at the end, right? And middle term you have to calculate using a and b. So you take a is equal to 6 and b is equal to 12. Then these numbers 6, 8, 9, and 12, right? So if you calculate using this formula, right? So twice AB divided by A plus B. So twice AB when A is 6 and B is 12. So 6 into 12, 74 into 2. 144 divided by 12 plus 6, 18. So if you simplify it, you will get 8. So the second number is A. The third number 1 by 2 A plus B. 18 by 2 is 9. And the last one is 12. So 6, 8, 9, 10. So these are in musical. So numbers which obtained from this formula, those are called musical. Why they are called musicals? This has some reason. Musical numbers related to notes are related to the notes of musical instruments, and so whatever things were there that time. So notes of musical instruments, right? That time were also there. So those numbers are related to that. Right? That's why they call musical numbers. And harmonical numbers are related to heavenly bodies in their motion. The heavenly bodies in their motion through space gave out harmonic sound, right? Harmonious sound. So that's why they are called harmonical numbers. You can see this sentence below this. Pythagoras believed that the distances of the astronomical planets from the earth were also in musical progressions. That is what he was thinking. And that the heavenly bodies in their motion through space gave out harmonious sound. That is what he believes. So that's why he termed these numbers in that progression. Probably he might be thinking that the distance from Earth to the other planets, they are in this progression. So that's why, right? He has termed them like this. Mathematicians believe that the Pythagoras belief is that the study of nature on philosophical conjecture. So whatever he was studying or whatever his followers were studying, they believe that the study is philosophical, right? Based on philosophical conjectures. and not on experimental observation. So they don't believe on observation. They studied on philosophical basis only. So that is what their thinking is there. After that, there was so many mathematicians. I took those who are important in the respect of history. So only those I have taken. Zeno was also there. He was born in Italy in 495 BC to 430 BC. Other than this place where Pythagoras was teaching in Greek, there were other places also. So Ila was one more place where mathematical teaching was done. So in Ila, it is Zeno and Xenophanes, right? This you can see here. So this Xenophanes actually founded the school in this Ila, known as Eleatic school, right? And that school was followed by Parmenides, then Zeno and Milesius. So Zeno was there, right? In 495 BC to 430 BC. Zeno, you can say Zeno was executed at Ila in 430 BC in consequence of some conspiracy against the state. So you can see that Pythagoras also people murdered him. His follower Hippasus was also drawn by his other Pythagoreans. Now you can see Zeno was also executed, right? So many mathematicians you can see they were executed or they were murdered because of something, right? At that time. The members of the Eleatic schools were famous for the difficulties they raised in connection with questions that require the use of infinite series. So see, the word itself, the sentence itself giving what kind of people they were there in this Eleatic school. Famous for difficulties they raised. So they are raising the difficulties in connection with infinite series, right? Related to infinite series, such as, for example, as well-known paradox of Achilles and tortoise. If you remember that, if you have gone through it. So tortoise, it moves very slowly, but Achilles was, I think, their god or something of that kind. And he was a man, you can say, like our Hanuman, right? With all kind of abilities with him. He can run faster. So you can think that there was a race between Achilles and tortoise, right? Something like this. That paradise they have discussed with the help of this one. So you may think that we know the story of tortoise and rabbit, no? So the same thing, Achilles and tortoise. So rabbit you can say, because rabbit ran faster than tortoise. So what these people are saying is, just okay. What Geno is saying is that if tortoise is suppose there is a race between Achilles and tortoise, and because tortoise is moving slowly, you give some concession to him. You ask him to start his race somewhere 100 feet away from Achilles, right? So if you consider like this, then he said that this Achilles, even though he is very fast, right, in moving, he cannot overcome tortoise. That is what he has proved with the help of this infinite series, right? When he was talking. So he says that this rabbit, in our notation, you can say, or in our own things, we can say, this rabbit cannot overcome tortoise, right? Even this tortoise is running faster. He has proved it mathematically in the form of infinite series, right? Because he is saying that because 100 foot away tortoise was there, so this Achilles has to go to that 100 feet first. By that time, tortoise will move somewhere some more feet away from him, so he will be away from here only, right? So Achilles was not overcoming tortoise in the first that 100 foots, I mean, right? And in second phase also, when he will reach to tortoise will be some point away from this one. So he says that Achilles will move near to tortoise, but when he come to the position where tortoise was there, that time tortoise will be some point away from him, right? So that means tortoise will always be in front of Achilles. Achilles will never overcome tortoise, right? So he has proved it like this using this infinite series. So difficulties he has raised in the form of this infinite series. So these people were like this. So Eleatic school people were like this, right? So Zeno was one of them. These paradoxes made they have given so many paradoxes. So this is one of them. These paradoxes made Greeks looks with suspicious on the use of infinitesimals. So when infinite terms will come, they were suspicious about it, right? Because they have got so many paradoxes, and ultimately lead to the invention of method of exhaustions. So they have found out this exhaustion method because they are suspicious about infinitesimals. So this is regarding Zeno. Okay. Archaeades was there in 400 BC, right? After the murder of Pythagoras, we find Archaeades recognized as the head of the school. So Pythagorean school head was Archaeades, and later that Hipparchus was there. So the Archaeades was the head of the school after the murder of Pythagoras. He was drowned in a shipwreck near Tarentum, and his body was on the shore. Punishment in the eyes of the more rigid Pythagoreans for his having departed from the lines of the study laid down by the founder, right? So he was not following whatever Pythagoras and whatever the oath they have taken. So that's why he was also murdered. Archaeades also was murdered by the Pythagoreans only, right? So in 400 BC he was the head. He is alleged that to have invented and worked out the theory of pulleys, right? In physics we can have, and credited it with the construction of flying birds and some other uh, ingenious mechanical toys. So Archaeades was constructed some mechanical machines, right? Mechanical toys for discussion of his discoveries, right? And therefore in that that means he's discussing the things with the other peoples other than the Pythagoreans. So he was away from the lines which was given by his founder, that means Pythagoras. So in that sense he was murdered. He introduced various mechanical devices for constructing curves and solving problems. Mechanical devices he was introduced, that was his contribution actually. Archaeades was also interested in astronomy. He thought that the Earth was a sphere rotating around its axis in 24 hours, and around which the heavenly bodies move, right? But he was thinking that the heavenly bodies are moving around the Earth, right? So that is what he was believed. Archaeades was one of the first to give a solution to the problem to duplicate a cube. If you know about duplication of cube, it means that whatever cube is given, right? You have to find out another cube whose volume is double than the cube which is given, right? But the condition is that you have to use only ruler and compass, right? You don't have to use any other thing, right? So Archaeades was one of the first person who gave the solution to this duplication of cube, right? So at that time these were discussing this insane problems duplicating the cube. Theodorus was another Pythagorean about the same age as Archaeades. He proved geometrically that the numbers represented by this one are incommensurable with unity. So they can be obtained with the help of unity. That is what we mean, right? We can study in geometry. Just a minute. Huh? Okay. So we obtain numbers using unity, right? Root 3, root 5 and obtain. No? So that is what you can say. This is discussed by Theodorus. Right? So many discoveries are there. I took only those related to numbers and very few, not all. Right? Now you can see EPS 420 BC belongs to Athenians, right? Hippias, he was not Ephesus. He was Ephesus, 400 BC. He is best known to us through his invention of an angle can be trisected or indeed divided in any given ratio. He not only said that angle can be trisected, but can be divided. He has used the mechanical devices invented by Archias, right? And Plato and other people later on objected on this one. So they said that the angle can be trisected. This is also another ancient problem. A given angle can be trisected using ruler and compass, right? So he has proved it. So we can trisect the angle. Not only that, he says not only trisected, at any given ratio we can divide the angle. That is what he has proved. But he has used the mechanical instrument that was invented by Archias and other people, right? Plato and those people were objected later on because when you use some mechanical device, you can trisect. Now also you can see any angle you can find, right? Any cube or any kind of cube or any kind of thing you can do, right? Now because we have much enough knowledge of mathematics. That time their condition is they have to use only ruler and compass, right? So they have objected. He has actually proved that time. Right? So he was known because of that. Then Anaxagoras between 500 BC to 420 BC. Anaxagoras taught the results of the Ionian philosophy. He was a teacher, so he was teaching whatever the Ionian philosophy was there and whatever inventions were there, he was teaching. The sun was larger than the god. That is what he was thinking. Due to this sinful act, he was convicted. So you see, this is one more Anaxagoras. Because he was thinking that the sun was greater than the god. God means whatever that time people were thinking. Actually, he was not used the word God. Some other word he has Philoponus, something he has used. Sun was greater than the Philoponus. I think Philoponus was a god that time, or maybe some maybe king of that place. I don't know exactly. So he thought that he's saying that sun is larger than, bigger than God, right, or that king. And people think that this act is sinful act, right? So that was he was convicted, and it is believed that in prison he has written a treatise on quadrature of the circle. Quadrature means what? You can trisect the angle, right? Trisection of an angle, right? Actually, his Anaxagoras paved the way for Athenian schools, right? Because after the death of Pythagorean and Pythagorean scattered, the center was the Athens, right? So he paves the way for school in Athens, right? That was Athenian school, right? Hippias, 420 BC, described as an expert arithmetician, but he was best known for angle can be trisected. That is what I told you in the beginning. Also, he was also one of the person who paved the way for Athenians. Right? This Hippocrates, Plato, and Theaetetus, right? They established actually Athenian school. Actually, Hippocrates invented or established the school, right? That was Athenian school. These three people were there. They established Athenian school. Hippocrates wrote the first elementary textbook on geometry. So he was the first to write a book on geometry. A textbooks on which probably Euclid's Elements was founded. So Euclid later on wrote a book, right, using the book which is written by Hippocrates, right? It is supposed that the use of letters in diagrams to describe figure was made by him. So he was the first person to use notation for see in the triangle we said ABC is a triangle. So A notation ABC, the symbols for the corners or something figures, geometrical figures. He was the first to use these letters in that diagram. See that in history it is said he was the first, but nobody knows whether he is first or is some people who are around him was studying or doing research or invention. They have done it, right? But credit goes to him, right? So right now also many people says we have invented. Actually, somebody might have also invented, but he has the first who quoted it. So when his literature came into exist or came in front of the others, they believe that he has done, right? So in that sense, exact thing was not there in history also. Nobody knows whether this is exact or not, right? But credit goes to him, you can say. So he was the first to give the figures, describe figures with the diagrams with the help of figures, right? Plato was born at Athens in 490, and his lifespan is 490 BC to 348 BC. Right? Plato, is a great thinker, right? You might have heard about Plato, and you might have read it about Plato also, right? He studied mathematics from Socrates, Theodorus, and Archias, right? So he was the student of these three people. Plato believed that the secret of the universe is to be found in numbers and its forms, right? Its forms is there. Numbers and its forms. That means multiplication and all those things, right? So Plato believed this one. So the secret of the universe can be found in the form of numbers, right? Because we are calculating distance of sun, moon, and all those things. So that way, the harmonic progression and all those things, they were taught in the form of numbers only. So that's why might be he's believing that he's a philosopher, so he believes in that, and he said that secret can be unfurled with the help of numbers. Right? See, these people were interested in the duplication of cubes. So this Hippocrates and all those we established Athenian school. So the people who were there in Athenian school, who were followers of Athenian school, they were interested in these three problems, in important problems: duplication of a cube, right? So if you have studied it or you have taught it, you can understood that the size of the cube, because all sides are equal in a cube, right? So if one side is invented, so the other will be equal, and we can find out, right? The cube whose volume is double than the given original one, right? So actually, duplication of cube in the form of a determining the size of the cube, right? One side of a cube, we can say, right? The volume will be length, breadth, and height. So once you know the one side, you can get breadth and height and the third side also, and you'll get the multiplication and you get a volume. So duplication of the volume can be done. Trisection of an angle, right? The second problem. And the squaring a circle. Squaring a circle means squaring a circle. So when you are given a circle with radius, can you find a square, right? Whose area is equal to the area of the given circle, right? So that is called squaring a circle, right? So these three problems, these people were interested whether this can be done or not. So some people have proved it and some people have disproved it, right? That time also. So they were calculating actually. They diagrammatically they are discussing those things, and they were interested in this problem, other than the other problems in mathematics, right? The Athenian and Sygians were thus designated to fail in all these problems. So they are not able to prove it. So they tried, but they are not able to. They failed in proving all this, right? Either that can be done or not done. So, but the attempts to solve them lead to the discovery of many new theorems and processes. So while doing this or solving this problem, they have discovered so many theorems and other processes. So that is their main contribution. As these problems are insoluble by Euclidean geometry. So you can see that these problems are not able to solve with the help of Euclidean geometry. Later on it was proved, right? So that's why. Okay. Then Eudoxus, Maniacisms, and Aristaeus, right? Aristaeus, right? They established Cyzicus school. So these two school, which one? Athens and Cyzical. So they were in the same period. So that's why. So I am not much about this Cyzicus school, right? But in that we can have Aristotle. Aristotle born in Stagira in Macedonia in 340 BC to 320 BC, right? 84 to 320 BC. So Aristotle was there, and he was a fellow in Cyzicus school, right? He was deeply interested though he was a natural philosopher. He was in natural philosophy, but he was simply concerned with mathematics and mathematical physics as supplying instructions of correct reasoning. So he has used mathematics and physics, mathematical invention and physical invention to give the reasoning for his philosophical thinking. So Aristotle was a philosopher. So he used to give reasoning. So he used mathematics and physical inventions for giving his reasoning, right? So then comes the Alexandrian schools, 300 BC to 30 BC. So this century produces three of the greatest mathematicians of the ancient time, namely Euclid, Archimedes, and Apollonius, right? So these were in 300 BC. So this Alexandrian school was actually due to Alexander the Great. The earliest attempt to found a university was made at Alexandria by this Alexander the Great. Richly endowed, supplied with lecture rooms, libraries, museums, laboratories, and gardens, and so on. Nowadays, you can see universities are like that, schools are like this. So this Alexander was the first person who was to think about such kind of schools. Before that, it was like ashrams and all those things, right? Like this, like that, right? Or maybe some form of gurus and shishyas of that kind, right? Alexander the Great had ascended the throne of Macedonia in 336 BC. So he was become a king at that time. At the early age of 20, only he was the king of that, or he was thrown as a king. And by the 332 BC, he has acquired, he conquered or subdues Greece. As conquered, I mean, he has win these areas after only 4 years when he became a king of that region, right? So he has acquired Greece, Asia Minor, and Egypt. So those regions he has conquered. So that's why we call him as Alexander the Great. After Alexander the Great in 323 BC, his empire was divided and Egypt fell to the lot of Ptolemy, right? So it was divided. Empire was divided between the few peoples, and Ptolemy was one of them. So Egypt went to Ptolemy's in the area of Ptolemy, who chose Alexandria as the capital of his kingdom. So Ptolemy was a man who used this Alexandria as a capital. But this Ptolemy is important for the inventions in mathematics. He determined to attract so far as he was able. You can say he was determined to attract learned man of all sort to his new city. So he was of that kind. So he want all learned person should be there in his kingdom. So he was thinking in that way. So he visited. He at once began the erection of the university buildings on the piece of ground immediately adjoining his palace. So near his palace only he built up university, right? Ptolemy, who wishes to secure for its staff the most eminent philosophers of that time, naturally turned to Athens to find, because Athens was the place where intellectuals were collected, were there. So once he became a king of that region, so he want all philosophers, a great philosopher should be there with him. So he went to Athens and other places also, and he asked them to come to his place. Under Demetrius Phaleros library, this fellow who was also from Athens, he asked him to come. So under this fellow, library was set up in that university, and there were about 6 lakh books. Books means that time books were not there. Collection of, you can say, some forms of inventions, right? So 6 lakh 6 lakh materials were there regarding the inventions in mathematics, science, and philosophy, and geometry, and all those things. So you can see how Ptolemy was great in that sense. The mathematical department was placed under Euclid. So see, here now there is a Euclid. So the mathematical department was placed under Euclid, who was the first, as he was one of the most famous of the mathematicians of the Alexandrian school, right? So he was the first person. His mathematics department of that university under him in Ptolemy's region. See, you have seen that Euclid many times. You might have heard about Euclid. So what he has did, that you can see here. He was born about 330 BC. About, I mean, not exact. He died about 275 BC. So his lifespan is not exact. So around 330 BC to 275 BC. He was well acquainted with the Platonic geometry. So he knows the Platonic geometry, what Plato and other people have done. But he does not seems to have read Aristotle's work. So it is believed that he was not aware about Aristotle's work. A most successful teacher when settled in Alexandria. He was the most successful teacher of that region. His successors and almost to his contemporaries, the name Euclid means the book or books he wrote. So they don't mean that he is a man. They believe that he is a book or books, right? Euclid, that time also. His contemporaries and other people. If you believe that he is not a person, he is nothing but book. He is known for that books. Euclid was noticeable for his gentleness and modesty. So he was a kind enough person. And what he wrote, which books he wrote, book means books, I mean. Euclid was the author of several books, but his reputation rests mainly on the elements. So this book is a series of books actually, elements. So it contains 13 books, right? So this element, now the other books also there are several books, and this is one of them. And this element is also a series of books, right? This treatise elements contains a systematic exposition of the leading propositions of the elementary mathematical geometry and the theory of numbers. But in geometry, conic section was not. You can think that Euclid was the first person who wrote everything from the Greek and the previous people, right? Ancient people. Whatever was mathematical thinking or astronomical thinking or geometrical thinking was there, he put in a systematic way in his book elements, right? So he was, in that sense, he was the first. So systemization was done by Euclid, right? In his book, you can see. About his book, we can see book 1 and 2, the work of Pythagoras. In one book, 1 and 2 book, work of Pythagoras is given. In book 3, the work of Epicurus were given. Book 5, work of Eudoxus were given. Book 5, 6, 9, 12, the work of later Pythagorean and Aristotle Athens. So whatever work done by Pythagoreans after Pythagoras and Athenian school, right? These were discussed in these books. And in book number 10, which on the last books of Theotetus, right? But probably much of its content is original, right? So in book 12, Theotetus' work is there, and many new inventions, original works are there in book number 10, right? So this is what the thing is there. Now book X, that means 10, on the last of Theotetus, probably, okay, this is repeated. The propositions in Euclid are arranged so as the form of chain of geometric reasoning, proceeding from certain almost obvious assumptions by easy steps to results of considerable complexity. The demonstrations are rigorous, often elegant, and not too difficult for beginners. So he has arranged them like this. So demonstration is rigorous, often elegantly written, and not too difficult for beginners. So systematically written books can be done by Euclid. Nearly all elementary metrical properties of space are investigated. Nearly all elementary properties were also investigated in these books. For 2000 years, it was the usual textbook. So later on, 2000 years, I mean, right? So you can see in the previous history, we have seen that there is a period of 70 or 80 years or 100 years. But now Now these books were about 2000 years. These were there, right? Still the books are exist, right? Euclid himself published a collection of problems generally known as the this data, I mean, right? This data. This contains 95 illustrations of the kind of deductions which frequently have to be made in analysis. So 95 illustrations were there. In sort of the elements, gave the principal results, and we intended to serve as a training in science of reasoning, while the data were intended to develop originality. So in data, you can find that new inventions were there. Euclid also wrote a work called De Divisionibus. Is a collection of 36 problems on the division of area into parts which bear to one another a given ratio. So this is there in this work, right? Which is apart from this the book elements, right? The first 4 books and book number 6 dealt with plane geometry. The theory of proportion is discussed in book number 5, and book 9 and 12 treat of solid geometry, and book 13 is a sort of appendix containing some additional propositions which would have been given put ultimately in one or other of the earlier books, right? So it contains appendixes, right? 13th chapter is appendixes, and it is also said that whatever books he has written, the books written at the later part of his life, right? Some of the books he was not able to revise. He has wrote it, but he was not able to revise them, right? Revision was not done. That is what is believed right now. Books 7, 8, 9, and 10 of the elements are given up to the theory of numbers, right? So in which you can find some discoveries in theory of numbers. In book 2, the numbers could be represented by lines and illustrated by concrete examples. So numbers were represented by lines. So that is what the contribution of the Euclid, you can say, or maybe some other people have done it. It was just represented in book number 2. This graphical method of using lines to represent numbers possesses the obvious advantage of leading to proofs which are true for all numbers, rationals and irrationals. So this way you can use for proving the results, right? And the results were be true for numbers, rationals and irrationals. I mean integers, rationals and irrationals. It is noticed that among other propositions in the second book, we get geometrical proofs of the distributive and commutative laws. So that time also this distributive and commutative laws were exist in the form of geometrical terms, right? Rules for multiplication and geometrical solutions of quadratic equations, which are like this: a into x minus a into a minus x, which is x square, that is, and x square minus ab. So geometrical solutions of this kind of equations was also there in the solution of the equation ax square minus bx plus c is equal to 0 and ax square plus bx minus c is equal to 0 are given in given later in book number 6, right? The results of the 5th book, in which the theory of proportion is considered, Euclid himself used this as a foundation on which he built the theory of numbers. So actually 5th book can be considered for the foundation of numbers. The treatment of the same subject in the 7th book is less elegant, and it is supposed to be a reproduction of the Pythagorean teaching. So in that book, it was just a reproduction of the Pythagorean teaching. In book 7, 8, and 9, Euclid discusses the theory of rational numbers. So rational numbers were discussed here. He comments the 7th book with some definition founded on the Pythagorean notation. In proposition 1 to 3, he shows that if the usual process in the usual process for finding greatest common measure of two numbers, the last divisor be unity, the numbers must be prime. So the primes were there in this one. Actually, primes were there. Okay, so GCD of the two numbers can be there. When you studied number theory, so in the beginning itself you can find Euclid algorithm. So finding GCD of two numbers. So that was there in the seventh book of this elements, right? Seventh book of the elements. Proposition 4 to 22 include the theory of fractions, which he bases on the theory of proportion. So fractions were there in two propositions of this book of 7. In proposition 23 to 34, he treats of prime numbers, giving many of the theorems in modern textbooks on algebra. So properties of numbers, so they are given there, right? In proposition, that means their number of primes are infinite and all those things which are there. But in proportions 35 to 41, he discusses the least common multiple of numbers. So LCM, we can say, and some miscellaneous problems he has discussed. Right? The 8th book is chiefly devoted to the numbers in continued proportion, that is in geometrical progression, and the cases where one or more is product, square or cube are specially considered, right? So continued fractions were discussed in this book number 8, right? Which were in geometrical progression. In 9th book, Euclid continues the discussion of geometrical progression, and in proposition 35, he enunciates the rules for the summation of the series of n terms. Though the proof is given only for the case where n is equal to 4. So the proof is given for n is equal to 4 only, but here general conclusion he has made. He also developed the theory of primes, shows that the numbers of prime is infinite. So that was the theorem which is at the beginning of your number theory. There are infinite number of primes. The proof also given by Euclid only. And he discusses the proof of odd and even numbers. He concludes by showing that the number of the form 2 raised to n minus 1 into 2 raised to n minus 1 is there, 2 raised to n minus 1 is there, where 2 raised to n 1 is a prime is called a perfect number. So numbers of this form are called perfect numbers. That is what he concluded in this book. In addition to elements, Euclid wrote the following books on geometry. So the geometrical contribution you can see here. An elementary treatise on conic section in 4 books. There are 4 books. A book on surface loci, probably confined to curves on the cone and cylinder. A collection of geometrical fallacies which were to be used as exercise in the detection of errors. So detection of errors, this will be used. A treatise on prisms arranged in 3 books. Right? Prisms were there. All these are lost. All these books were lost. Euclid published a book on optics. Now these books were not now exist, but it was written somewhere. So that's why it came into existence. But what are the contents that was not there? Euclid published a book on optics, created geometrically, which contains 61 propositions founded on the 12 assumptions, right? So book on optics also he wrote. He also wrote the phenomena. He wrote also on the phenomena a treatise on geometrical astronomy. Euclid also composed a book on the elements of music known as Sextio Coninis, which deals with musical intervals, right? So he has wrote these books. So this is the contribution of Euclid, you can say. So systemization of the inventions made by the previous people, and whatever the new things were there, that these were discussed along with their proofs. So that was given in book by Euclid. Archimedes was there later on in 287 BC to 212 BC. He went to the University of Alexandria. His mechanical ingenuity was astonishing. Archimedes, like Plato, held that it was desirable for a philosopher to seek to apply the results of science to any practical use. But in fact, he did introduce a large number of new inventions. So he was of belief that not only you have to study those results of science, but you have to use them in practical use, right? And you know what he has invented, Archimedes' principle. The work for which he perhaps now best known in his treatment of mechanics of solid and fluids. So this is what Archimedes done work in physical sciences, right? Most of these were, but based on mathematics, right? You can see a solid. But he and his contemporaries esteemed his geometrical discoveries of the quadrature of a parabolic area, right? So parabolic area can be trisected of a spherical surface, and his rules for finding the volume of a sphere as more remarkable. On plane geometry, the extant work of Archimedes are in three numbers, namely measures of circle, then quadrature of parabola, and on spirals, right? On geometry of the three dimension, the extant work of Archimedes are in two numbers, namely sphere and cylinder, conicoids and spheroid. On arithmetical, on arithmetics, Archimedes wrote two papers. One was on principle of numeration. This is now lost. The other was called Sand Reconer. On mechanics, the extent work of Archimedes are in two numbers, namely his mechanics and his hydrostatics. He wrote a book, this one, on construction of celestial spheres. So you can see that whatever his discoveries are there, so these are related to science, physical sciences. You can see here on this side, Archimedes was killed during the sack of the city, which followed its capture. So the city was captured in spite of the orders given by the consul Marcellus, who was in command of the Romans. So he was a Roman commander. He has ordered that you should not kill Archimedes, right? But he was killed. That his house and his life should be spared. That is what the order by this king was given, right? This consul was given, but still he was killed, right? It is said that a soldier entered his study room while he was reading a geometrical diagram. So he was regarding a geometrical diagram drawn on the sand of the floor, right? Drawn in sand on the floor. So on the floor, he has made some diagram, geometrical diagram with the help of sand. And in that room, that soldier entered, which was the usual way of drawing the figures in classical times. That time they were using this science to draw the diagram. Archimedes told him to get out of the diagram. So that soldier was entered the room, and he was on the diagram. So geometrical diagram, he was drawn on Archimedes was has drawn on the floor, and not to spoil it. That is what Archimedes says. Archimedes says, get out of the room and don't spoil my diagram. The soldier, feeling insulted at having orders given to him, whatever orders he has given, so he thought that this is insulting, right? And ignorant of who the old man was, killed him. So that soldier killed the Archimedes, right? That is the story regarding his death. Okay, Apollonius 260 BC to 200 BC. Chiefly celebrated for having produced a systematic treatise on conics. So Apollonius produced a systematic study of conics. Diophantus, date of his carriage is uncertain. Dipentonian equations, you know. Polynomial equations solution should be integer, right? Diophantus, you are known to him regarding this kind of thing. Diophantus wrote a short essay on polygonal numbers, a treatise on algebra, a work on prisms, which is lost. The polygonal number contains 10 propositions. In this, he reverted to the classical system by which numbers are represented by lines. So this was also representing numbers by lines. His chief work is in his arithmetic. This is really a treatise on algebra. Algebraic systems are used and problems are treated analytically. So work is arithmetic. Chief work is arithmetic, and these things were done in that. The following as characteristic example is one of the examples. Find four numbers, the sum of every arrangement, 3 at a time being given, say 22, 24, 27, and 20. So find four numbers. You have to find four numbers. And when we rearrange them, their addition will be this one. Rearrangement 3 at a time, right? So 4 out of 3 I have to take. So how many rearrangement will be? 4 will be there. So and their addition will be this one. So let x be the sum of all 4 numbers. And the numbers are x minus 22 and 24, 27 and 20. And when you take their addition, x is equal to this. And if you simplify this, x is equal to 37. X is 31. And when we subtract these numbers, you get 9, 7, 4, and 11. So those numbers are 9, 4, 7, and 11. So these are the 4. So that is what things were studied by this Defenders in his treatise, right? Such kind of problems he has this. Divide a number such as 13, which is the sum of 2 squares, 4 and 9, into 2 other squares. So number 13 you have to divide. He says that since the given squares are 2 square and 3 square, right? And this 4 square is 2 square, 4 means 2 square, 9 means 3 square. He will take x plus 2 square and mx minus 3 square as the required square, and will assume m is equal to 2. While assuming m is equal to 2, therefore this will be 13. So x is equal to x is 8 by 5. So values of x can be calculated, and the other numbers are 324 by 25 and 1 by 25, right? So the square and sum will be 30. But these are rational numbers; these are not integers, right? Find 2 square such that the sum of the product and either is square, right? Find 2 square such that the sum of the product and either is square. He also proved this one. So these are the kind of problems. The proof is also given in the book. I have not taken here. And so many problems are there. I have taken only 2 or 3 to just give the glimpse of what he has done at that time. He has also proved the following. No number of the form 4n minus 1 can be expressed as the sum of 2 squares. So no number of this form. So when we put n is equal to 1, this is 4 minus 1 is 3. So 3 cannot be expressed sum of the 2 squares. So general formula is there 4n minus 1, where n is based from 1 to 1, right? So these number cannot be expressed sum of 2 squares. No number of the form 8n minus 1 can be expressed as sum of 3 squares. This is sum of the 2 square. This is sum of the 3 square, right? So that is now preparing the basis for format work, right? Okay, this one is there, and later on, an imperfect copy of the original work was discovered in 1462. It was translated into Latin and published by Xylander in 1575. The translation excited general interest, right, at that time. And later on, the Benjamin schools were there, 641 AD to 1453 AD. After the capture of Alexandria by Mohammedans, the majority of the philosophers who previously had been teaching there migrated to this place, Constantinople, right? In the 14th century, we find the names of 3 monks who paid attention to the mathematics. In between, there is not much mathematics was developed. That is what the authors claim, right? But in that, during that period in India, much of the things were discussed regarding numbers, right? We'll see that later on. After the capture, okay, in the 4th century, we find the names of 3 monks who paid attention in mathematics, namely these 3 people. This was the first, Maximus Planus. He wrote contemporary on the first 2 books of the arithmetic of Diophantus. So the book was written on the work of Diophantus and based on arithmetics only. A work on Hindu arithmetic in which he used the Arabic numerals and another on proportions. So Hindu arithmetic was wrote in a book by this monk, right? Who is in 14th century, I mean, right? 14th century I'm talking. So directly BC to AD now there is a gap. So in between there were Hindu and mathematicians, right? Or astronomers, we can say. We'll come back to those later on. Balram, right? So he was author of the work Logistic and on the Greek method of calculations, which Greek translated numerical fractions, right? This was wrote by this monk. Then this Argyros was also the third one. He wrote 3 astronomical tracts, one on the geometry, one on the arithmetic, and one on the trigonometry. Right. So these monks have written the books. After Diophantus, not much progress was made in the theory of numbers until the 17th century. So this was a gap because there were wars in all over the world between the civilizations. So that's why not much mathematical thinking or other thinking was there. But in Indian Hindu area region, the discoveries were there. Although there is some evidence that the subject begins to flourish in the Far East, especially in India, in the period between 500 AD to 1200 AD, right? Okay, let us see this. Now, Middle Ages. So we'll come back to that region, 600 AD to 1200 AD. Boethus, right? Rome, and 470 AD to 560 AD. He introduced the public use of sundials, water clocks, etc. Right? So whatever those things were there, so these were introduced to the public, right? Before that, it were to those schools and all those the kings only, right? Now it becomes public by Boethus. His geometry consists of the enunciation of the first book of the Euclid, right? Based on Euclid's. His arithmetic is founded on that of Nicomas, right? But arithmetic was found on Nicomas. After this, Arab initiated acquiring scientific knowledge. To conquer diseases, the study of medicine was then confined mainly to Greeks. In the Arab region, there were diseases. So to get treated the people, these Arabs asked the Greeks to come and treat them, right? So that is what I am saying here. Confined. The study of medicine was confined mainly to Greeks and Jews that time. And many of these, encouraged by the caliphs, settled in Baghdad. So that caliphs thought that these people should come to Baghdad or maybe in Arab region, and they treat the diseases which were there. So these people came to Arabs now, the Arab area. The Arabs remarked that the Greeks rested their medical science on the work of Hippocrates, Aristotle, and Galen, right? So they understood that their medical science is the result, the knowledge is based on the work of these 3 people, right? And therefore the books were translated. Their books were translated into Arabic by order of the Caliph. The name is also given around 800 AD, right? So Caliph ordered that whatever books were there with Greeks and other people, Jews, you have to convert them into Arabic, right? So in 800 BC, they converted them. The translation excited so much interest in his successor. So successor of the Caliph, Saint 830 to 833, he sent a commission to the place where the center of intellectuals were there to obtain copies of many scientific works as was possible, while an embassy for a similar purpose was also set up in India, sent to India. So people were sent to India also to collect the work, right? So that was the Arab Khalif were done, right? So whatever books were there, they have translated into Arabic. Whatever Indian things, Hindu things were there, they were also converted, translated into Arabic, right? So in this way. So Hinian and his son Isaac ibn Hinoin revised the translation before they were finally issued. So before issuing to the people or the other people, they were translated. But these people were not much aware about mathematics, right? So they have made some mistakes also. That was quoted in the book, but we are not going into that much discussion. Tabit ibn Qura shortly published fresh editions, which thereafter become the standard text. So because there were some corrections in those books, which was revised by this Hinoin and his son, after that Tabit ibn Qura revised those, and then these become the standard. Before the end of the 9th century, the Arabs obtained translation of the work of Euclid, Archimedes, Apollonius, Ptolemy, and others. So most of the work is translated into Arabic language now. The Arabs had considered commerce with India and a knowledge of one or both of the two great original Hindu works of on algebra, and had been thus obtained the Caliph of Al Masur, something like. Though it was not until fifth or sixth year later they attracted much attention. They captured that the work, they obtained that work, but they have not used it for 5-6 years. So Hindu work is also there. Hindu work was there in between that region, right? Okay, what is that Hindu knowledge? The Hindus, like Chinese, have pretended that they are the most ancient people on the face of the earth. So that is our belief. We Hindu and Chinese were believe that we are the first person on the earth, and that to them all sciences own their creation. So all sciences were created by us. That is what we believe. That was written in the book, right? That is what is written in the book. And nowadays, now we are in unfurling the things which were quoted there, and we find that actually we people did some work before this Pythagoras and all those things, right? Aryans were there in India, right? Before Pythagoras. So that time we had some mathematical creations, and those were come to Euclid and all those right now, Arabs and all those, right? So that was Pasan. In the later half of the 5th century or in the 6th century, tribes of Aryans entered in India by northeast frontier and established themselves as a ruler, right? In 5th and 6th century. Aryabhatta, right? See, now the work of Aryabhatta we can see. The chief work of Aryabhatta is Aryabhatiya. So he wrote a book which consists of mnemonic verses embodying the enunciation of various rules and propositions. So it was written in the form of poet, right? Poetic way of writing was there in the book of Aryabhatta. We know it is in terms of slokas and all those things, right? The book is divided into 4 parts. Of these, 3 are devoted to astronomy and the element of the spherical trigonometry. The remaining part contains the enunciation of 33 rules in arithmetic, algebra, and plane geometry. So this book is divided into 4 parts, in which this is. Aryabhatta regarded himself as an astronomer and studied mathematics useful to him in his astronomy. In algebra, Aryabhatta gives the sum of the first, second, and the third powers of the first and natural numbers, right? Sum of the first, second, and third powers of natural numbers. Sum of this is what is given. The general solution of a quadratic equation, general solution, he was invented. The solution in integers of certain indeterminate equation of the first degree equations were also there. Quadratic equation, first degree is there. His solution of numerical equations have been supposed to imply that he was acquainted with decimal system, right? Decimal system was known to him. In geometry, he gives a table of natural signs of angles in the first quadrant, proceeding by multiples of 3 into 3 by 4 degree, defining a sign as the semichord of the double of the angle, right? Assuming that the angle 3 into 3 by 4 degree, the sine is equal to the circular measure. He takes for this value is 225, the number of the minutes of angle. He then enunciate a rule which is equivalent to the statement sine of n plus 1 into alpha, it is into minus sine n alpha is equal to sine n alpha into sine n minus 1 alpha minus sine n alpha into cosec alpha, where alpha stands for this one, 3 into 3 by 4 degree. So working with his formula, he construct a table of sines and finally find the value of sine 90 to be 3438. So he has constructed the table of sines. This result is correct if you take pi equal to 3.1416 as the value of pi. 3 point it is. And it is interesting to note that this is the number which is in other place he gives for pi. So He has given the value of pi also. Brahmagupta in 598 to 660. He wrote a work in verse
Excuse
of.
me, sir. Sir,
Yes.
Actually, we are just running out of time.
Yes.
Uh, will it be possible to summarize in next 5-10 minutes?
Yes, I will try to summarize it.
Okay, sir. Okay, sir.
So now you can see the work of Brahmagupta. He wrote a work in the verse entitled Brahma Supta Siddhanta. Right? The Siddhanta or system of Brahma in astrology. In these two chapters are devoted to arithmetic, algebra, and geometry. The arithmetic is entirely rhetoric. Most of the problems are carried out by the rules of three. Right? In algebra, he has done this one. He worked out fundamental proposition concerned with an arithmetical progression and solves quadratic equations. Brahmagupta finds solution in integers of several indeterminate equations of first degree. He states one indeterminate equation of the second degree, namely this one, and gives the solution like this. Curiosity enough, this equation was sent by Fermat as a challenge to Wallis and Lord Brouncker in the 7th century, and later found the same solution as Brahmagupta had previously done. Brahmagupta also stated that the equation y square is equal to nx square minus 1 could not be satisfied by integral values of x and y unless n could be expressed as sum of the squares of two integers. In geometry, Brahmagupta proved Pythagorean properties of right angle triangle. He gave expression for area of triangles and of equilateral inscribed in a circle in terms of their sides, and he showed that area of the circle was equal to that of rectangle whose sides were the radius and semi-perimeter. He also determined the surface and volume of the pyramid and cone. Bhaskara was there, so he has done work in, after Brahmagupta. He was the head of the astronomical observatory region. He wrote Lilavati. You know, I think you might be knowing more about Brahm Bhaskara, right? Bhaskaracharya, one I mean, Bhaskaracharya. He wrote Lilavati and all those things. It was there. And what he has done, that is given here. I will ask your coordinators to share the presentation so that you can read it out. After Brahmagupta, the development of mathematics in Arabia, after this, because we have seen that in Arabia they converted the work of all this Pythagoras and Euclid and all those things and Hindu work. This is given by this Brahmagupta, Bhaskara and other people, right? So then they converted into their Arabic language and then they have made some contribution. So the contribution is here. Al-Kharizmi was there, right? Then Tabit bin Qura that I showed you. Then Al-Qayami was there. After that, this work was introduced to Europe. So whatever work was done in Arab, that is now introduced to European countries. It is starting from Spain and it went into other places. Solid work, that means all work together, right? That was went to Europe again. And then these people were there. Then Gerard was there. During the 13th century, there was a revival of learning thought throughout Europe. So you can see 13th century it was there. Fibonacci 1155. Regarding Fibonacci, you can see Fibonacci series and all those things were there, right? And then Jardinus was there, a German mathematician. So once the knowledge went to Europe, then these people have done some other work. Roger Bacon was there, and this was how the representation of numbers were there in this area in the periods, right? In Devanagari, you can see in year 950 AD, numbers were represented like this. In Arab, go for Arabic numbers, 11,000 AD, numbers were like this. From Misr, German origin, this were there. European, they were written like this, right? And we can see. So these numbers were converted like this. After the introduction of zero, the rules of zero was given by Brahmagupta. So it was there in my presentation, and after that zero was there in these numbers. In 19, this region, this period now you can see modern mathematics, where number theory came into use as a subject, right? René Descartes was there, 1596 to 1650, right? So I can read it up regarding him. His main contribution is analytical geometry, right? René Descartes. Then Pascal's we can see 16 at 16 Pascal went to conic section he wrote, and then he has done some work, machines and all this thing, arithmetical machines and all that, right? He was known as a father of, you can say, a computer, right? So and then Fermat 16,001 to 1651. So you know much of the work was done by Fermat in number theory, right? You can see this here. You can see if P is a prime and A is and A with the prime to P, that means GCD of A and P is 1. Then A raised to P minus 1. Minus 1 is divisible by P. That means A raised to P minus is congruent to 1 modulo P. So congruence relation came into exist this in this area, you can say, in this period when Fermat was done some work, right? And most of the theorems which were there in number theory, those were can be done. Those were invented by Fermat and proved by Fermat. Right? Some of them are there in the done by previous people. Their proofs were systematically given by Fermat. Right? These are some examples which were given here. And then after that, Gauss was there. Carl Friedrich Gauss, 1772 to 1855. The greatest mathematician all the times, right? You can say the first word itself indicate that how great he might be, right? So the things which were there for Gauss, which is written here. After Fermat, these people have done some work. That is what it is given there. Gauss book was also there. Then just a minute. These are the things we Gauss. So whatever content of this presentation is there, it is taken from this book, A Short Account of History of Mathematics by W. Ross Ball, right? This was published in New York, and it is available on Google and in the form of ebook, and it was released in 2010. Actually, the first book was written, first edition was written in 1888, right? 1888. Now it is 2010. Ebook is released on 2010. So whatever content is there in this presentation, that was taken from this book only, and some of them are from net also, right? And some of the points are also taken from the book by number theory book by this what is that Newman Zuckerman, right? So that's also considered. So I think this is the end of presentation from my side. Thank you very much for your kind patience and hearing. Again, I am thankful to the convener and principal of the college for giving me an opportunity to discuss my views on this number theory historical review. Thank you very much. Hello.
Thank you, sir. I think I wish we could have kept more sessions on this. Maybe next time we will include some more sessions on number theory. Okay. If participants have any query, they can ask, sir.
Too much things are there in my presentation, and you can read out the book. You can see that so many contents are there. I have taken only few out of it. If you have any query, you can ask me. Otherwise, you can consult with the book.
Participants, any question?
Sir, just one question. May I get in, sir? 1 second.
Yes, sir.
Yeah. Sir, in number theory, like this is basically the history of number theory and history of mathematics altogether. I just wanted to know for universal forms, like, you know, this one, what is that? Quadratic forms, like modular forms are later on, but quadratic forms and then universal form, basically, sir. Is there any suitable book? Which book is to be referred for this one? Sir? Any idea? Like, universal forms.
Yeah, you can see that some work is done by Gauss regarding reciprocity and all this.
Correct. Gauss.
Probably you can find the work of Gauss,
Correct, sir.
the book he has written on arithmetic, and you can find some of the things, historical things in that book.
Yes, sir. Thank you very much, sir. And Kshitish, sir, 1 second. Who is around? Kshitish, sir.
Yes, sir.
Yeah, I just would you give me little opportunity to thank the whole department and this thing within short while, because within short span of time, I obviously not a good speaker, but little thank. Just could I proceed further?
1 minute, sir. 2 minutes. Professor Chaudhary, sir, it was a comprehensive talk on a historical development of the ancient branch of mathematics, number theory. Your presentation was really well researched and exhaustive and full of historical anecdotes. We are thankful to you, sir, for taking out your valuable time for our workshop. And with this, I conclude that this session ends here. This last session of our workshop ends here. And sir, if possible, you can switch on the video and we can have one group photo.
Yes.
Thank you. Thank you, sir. Thank you. Okay. Now, sir, you can give your feedback.
Somebody want to say something, no? So
Yes, sir. Yes, sir.
Would I come in?
Yes, sir.
Yeah. Thank you very much, Ajay, sir. Yeah, thank you very much. I won't take much time of yours. Only the thing is that, sir, actually what happens, like, theory and, theory part or, teaching content and all, we have lot many books, like we can refer, those who are interested can go for this or that or some other. But sometimes history, history becomes very difficult to grasp with and very difficult to believe in actually. So when some authentic people are talking about it with the help of their own research, it is a very different altogether. So first of all, I'm very thankful to the whole department of RJ College, as I always happen to be, and definitely very thankful to its indispensable and very passionate organizers. I'm very thankful to Sanket sir as well, who I was keep insisting him for sending this one link and all, and he happens to be my FB friend, so I got to know from FB. And then point is, sir, like, sometimes, for example, I don't know how long I should talk about it, but even zero is considered to be the invention of India, but sometimes there are very ambiguous and there are very vague kind of historical events about it. Like, some people saying Aryabhat invented it. Some definitely will give credit to Brahmagupta, this and that. Whereas, like, some of the historical events are saying Acharya Pingala was one who actually used zero very first time. Some of the places I know, I don't have that historical even knowledge much, but what I'm actually trying to say is, like, when some able or capable people, those who have done research on it, and if something is coming from their side, it becomes like gospel truth, sometimes, because everything Google uncle cannot tell us everything, because there may not be things up to date, because these things are also updated by some mortal, like human being themselves. So that was, I just wanted to tell you, sir. And one more thing, last but not least, I'm very thankful to my dearest friend, Professor Indra sir, who happened to be always great support for me throughout my, like, as a student and later life as well. I won't extend much, sir. I'm so sorry because time is already up, right? And I'm so sorry you gave me a chance to thank to the whole department. Thank you very much, sir. Thank you.
Just a minute, Rajendra.
Yes, sir.
See, what you said is this is okay, but see, nobody give you the precise answer to your problems, because
Definitely.
nowhere it is written who has invented zero, whether
Correct.
the years and the things were written in the
Correct, sir.
history book were correct or not.
Exactly.
They don't have any proof. They are obtained
Definitely.
from somewhere and they just giving to us. So on
Correct,
that we
sir.
are following.
Correct,
Right?
sir. Correct,
So
sir. Correct, sir.
it's
Agreed,
impossible
sir.
for anybody to give. Even those who are studying
Yep.
history, those who are doing
Correct.
research in history, they are
Correct.
also unable to give you the exact thing.
Yes, sir. Yes, sir. Definitely, sir. Very much agree. Yeah. Very much agree, sir.
Yeah, I just want to, the zero concept, I just want to add something.
Yeah.
The only known earliest place where zero is used in written form is in India. Whether we invented zero or not, it's not clear. That's not historically established. But the only written place, only written document, you can call it, where zero is used to say something is in India. There is a Gwalior fort.
Yes, sir. Yeah.
And there is a temple in the Gwalior fort.
Yeah. Zero is written somewhere there. Correct. Correct.
So there is a plaque, small stone outside it.
270 or something. Correct. Correct.
Would you like to say something, or shall I continue saying something?
Yes. Yes. Yes, sir. You continue, sir.
Okay. So that small stone has that the area of length of this temple is so much, breadth is so much, and that is the only earliest known place where zero appears as a place value for something. The 270 or something feet or yards or some such thing. So if you, and it is acknowledged by the whole world that that is the earliest known document, earliest known proof of zero being used by human beings. Okay. So more than that, I don't want to say anything. I call it as temple of zero.
But what is the period of that? What is that period?
You
Is
should,
it in UD or BC?
no, it's in Gwalior is a temple. Okay. And that is, it's after our regular period AD, sometimes in AD, I think. It's not very old, I think.
It's very clear that Brahmagupta has given the rules of zero. It was,
But there are no written documents as such. Only we believe everything, as you said yourself. So let us not go into this controversy of who invented what, when, kind of a thing. But there are some known facts, known historians who say this is this and this is this and this is this. So let us not spend too much time on trying to ascertain who did what, kind of a thing. Right? Of course, if you can do research and find it's okay. But I think there are much more mathematics to be discovered, and rather than saying who discovered what, kind of a thing. So thank you.
Sir, one question from IK Rana, sir. One question, sir, please. If you give me a chance. One question.
Okay.
Yeah.
I revealed my identity.
Yeah, just one. Yeah, sir. Because I wanted even to talk to you yesterday itself, but I couldn't because of the short of time. Sir, this one again, because we are actually delving into history, so I'm so sorry if suppose I'm not following the protocol you actually fixed up, that one should not go about history and this and that. One should only study mathematics. What I wanted to know, sir, we were talking about yesterday log and exponentials. So could I simply because from you I just wanted to know, could I say, sir, is it true or something whether it is all right that exponential was basically found, as you told, that log is because of that integration, but exponential actually came out because of that compounding kind of thing, compound interest, and by that you applied that limiting kind of process, something like that?
It might have come. I don't know much about I have not delved into the history of the exponential function as such.
Correct, sir.
But it's quite possible that human beings, when they started sort of investing money and found that simple interest and compound interest might have led to powers of something and exponential things. But
Correct.
exponential function e raised to power something, that is, say, even if you take compound interest for 10 years, 15 years, 20 years, and nobody bothered about probably after 50 years, because transactions and the business won't go more than 15 years between two human beings probably. But the beauty of mathematics is you can let n go to infinity, and then from the compound interest, you can get the exponential powers, e raised to power x or e raised to power tx. So that is the beauty of it actually. And it's not only the compound interest and the simple interest, the growth of bacteria.
Correct, sir. That is what I wanted to say. Yeah.
Yeah, it's the problems of growth and decay.
Decay and growth.
Exponential functions find use, and something grows very fast, so number of n goes to infinity kind of thing. No, so for very very large, how do you estimate these kind of things? So that's where and modeling growth and decay problems, exponential comes into picture. But historically, if you want, because this is about the history as such, whether exponential function came first or whether log function came first, I have no idea about it. It's probably worth exploring. We know that exponential is the inverse of log and log is the inverse of exponential. So anda pehle aaya ke murgi pehle aayi, pata nahi. We don't know. So who gave birth to what? Whether it was exponential and then saying that the inverse is exponential, or whether exponential and the inverse is log. But it was only after calculus was put on firm grounds, it was clear that we can define log function very rigorously using fundamental theorem of calculus and prove it is a one-to-one onto function. And then the inverse is taken as the exponential function. And one can prove all these properties very nicely just by elementary calculus. And then also one can define what is called, if you extend integration a bit into what is called when the functions are not necessarily bounded or domain is improper integrals, then you can define what is, see again trigonometric functions, the same problem comes, derivative of sine is cos, derivative of cos is sine. So which one you define, right? So what one does is, instead of defining sine, you define sine inverse over minus pi by 2 to pi by 2 as a integral of 1 over 1 minus x square, and then give all the properties of sine inverse as a 1 onto function, and then you define sine from there. And once you have defined sine by using inverse function theorem, you can define derivative and so on, and cos function. So that is the route one follows to define trigonometric functions using calculus. I'm sorry, I went into too much into.
No, thank you very much, sir. We wanted actually. Anyways, yeah.
Okay.
Thank you. Yeah.
Thank you, sir. Now I request our HOD Professor Miri Joshi to speak few words and to give concluding remarks about the workshop.
Dear all, it's my great pleasure to be a part of this well-organized national workshop on the historical development of mathematics. Due to the work of eminent mathematicians and scholars, mathematics has evolved into a beautiful subject. The development, especially the historical development of each topic in maths, fascinates those who study it. So this topic was very much apt, and we all like it as mathematicians, as teachers, students. We always like to know how a thing has evolved, and it gives us great pleasure in knowing that so many people work. So, and due to that, we are understanding the topics. So it was a wonderful. I thank all my dear colleagues, Indra Singh Saud sir, Dr. Sanket Tikare, Ajay Shukla sir, for having arranged expert resource persons from all over India who by their expertise enriched us. I thank you for all your efforts that you have done. I also thank all our TYBSC students who hosted many of the sessions so very well. So thank you, students. I also thank our management, the director, madam, principal, sir, for all the support. I thank all the resource persons who took time and accepted our invitation and enriched us by their sessions. I also thank all the teachers and student participants who, with their lively participation, made this workshop a success. Thank you all.
Thank you, ma'am. Participants, your certificates, I think within 10 days, I will post in the Telegram group. So within 10 days, we will post all the certificates. And please try to fill all the feedback forms by today evening. It will be a great help. So thank you very much. Thank you, everyone. So I think I will end the meeting here.